Okay, give me a second. I will switch to my SmartPLS software. Okay, now you are in my SmartPLS software. Let me take this example. I will close the old example. Give me a second. Give me a second. Close this one, and then I close this one, and I use this one. Okay, so right now you can see my SmartPLS software. I use back the data set from data set provided by the SmartPLS team. We have competence, we have satisfaction, which is the single item which someone asked just now, and we have likability and loyalty. Okay, if you run a PLS algorithm, which is the traditional, you still produce the reflective results on your loading and so on. Okay, let us look into a few results. Okay, let us look into just the result of this one. Okay, let me highlight in color so that we just focus on this value. Okay, we don't focus on other value. Let me highlight in pink. Okay, we just highlight two construct. Okay, based on the correlation and based on the loading. Okay, I will tell you the result will be different. Okay, but again, there's an advantage of doing PLSC. I can see the advantage, but it is not necessary for you to do PLSC. But I can see the advantage. Okay, so let us just look into the two construct. We have likability, we have loyalty. The path coefficient of likability to loyalty is 0.342, and then you have likability, where loading is 879, 870, 843, 833, 97, 843. Okay, maybe we look into likability, which is 879, 870, 843, and the coefficient is 342. Maybe we just look at this few value. Okay, right now we run a consistent. We click on consistent PLS algorithm. We just run consistent PLS algorithm, start calculation, and here it goes, where your value here 0.3 right now. When you correct the correlation, the value become 0.532. And just now, this one is not significant, right? In PLS algorithm, now becomes significant, 0.1111. It's considered quite significant there, but I'm not sure. I just run just PLS algorithm. But when you look into the value here, the loading value here seems to be like a bit higher, and it changes a lot. So there's a difference between of running the PLS and PLSC. Okay, when you run the PLSC, it will produce the true reflective value. Okay, but let us back to the traditional PLS algorithm. Okay, you see 342. Now I change to PLSC, it becomes 532. Okay, the result different. Okay, we go back to PLS algorithm. The value here is 879 on the likability item, the loading 879, 870, 843. Now we change to PLSC algorithm. It becomes 855, 773, 735. It will be different. Okay, but the loading in PLS always estimate higher. Okay, sorry, what I mean is the loading in PLS, traditional PLS estimation is always higher, but when you comes into correlation, it will always lower. Okay, it will be always lower. Like for example, when you come to correlation, it is lower, 532. Okay, but when you come to loading, it will always higher in PLS compared to PLSC. PLSC, the loading is always lower because it produces the true value. Okay, so because of that, this is how you can run your PLSC. Even you can run your PLSC with your consistent PLS bootstrapping to get the structural model results. And here you go, you get your results. Your value, which is a p-value 4.421, and yeah, you can get your results. And even if you want to do more advanced stuff in PLSC, you can do a multi-group analysis, as well as you can do a measurement invariance in consistent permutation. So it's very easy and convenient. But what I want to highlight to you is the result will be different. Okay, back to the PLS algorithm. Okay, if here 879, 870, 843 using the PLS algorithm, but right now go back to PLSC, it will be 855, 773, 735. You see it drops, right? So you can see that if you use traditional PLS algorithm, you could retain a lot of good item of reflective because the loading is always higher. Okay, the loading is always higher. Why the loading always higher? Because it takes consideration of total variance, where all the errors are actually correlated. As you can see in just now the figure of B, the composite modeling, where reflective formative, the beam figure, the errors is actually correlated. When you actually correlate your error, your loading will shoot up. So that is how total variance looks like for a construct. But when you move into PLSC, your errors no longer correlated. Therefore, your loading is always lower. But because you correct reliability, which is using the row A, which is, if you go to report, you can see the result of your row A, as you can see in the middle, Chrombush alpha, and then row A and composite reliability. Because you correct the row A, it will produce the true correlation value of likability to loyalty, which is 0.532, which is slightly higher than the normal traditional PLS. So that is a bit about PLS consistent. I hope you know on how to use the PLSC. It's very easy. I know some people will say that why you need to know the formula, you can just click. But again, the formula itself tells you why it corrects reliability, and then why it will then correct the correlation effect between two construct X to Y. And that is the reason why you could see likability and loyalty, the correlation shoot up from 0.4 to 0.5 because it corrects reliability. At the end, it will correct correlation. So that is how you look into the PLS consistent. So I hope you're clear with that. I haven't finished yet, so I will stop share this one first. Now I go back to my slide, which explain a bit more about this common factor modeling as well as PLSC. Okay, so go back to my slide. If you want to know more about this PLSC, this is not a perfect piece of paper, I would admit, because it was then when I get my first job in Universiti Technology Malaysia. I was a senior lecturer there. I was starting my career as young researcher. This is my first attempt of writing a method paper. So it's my first paper with my team, Mumtaz Ali Memon, Francis Chuah, Hiram Ting, and Prof. Ramayah. We was writing this thing, and it was still very new to us in PLSC. It is not a perfect and masterpiece, but there's one thing that I want to highlight here is like, which is I still think is still valid today, which is the guideline that I proposed, which I still think valid. Maybe some people might not think valid. It's like when you do a consistent PLS, which is running the PLS consistent, one thing I want to highlight is more on the model fit. Okay, in PLSC, it is important for you to run model fit because we are moving into the world of confirmatory. Because when you are doing a modeling, you need a confirmatory model fit type of criteria. And some of the famous criteria that you can see is the SRMR, and this was borrowed by covariance-based SEM like Amos, Lisrael, and M+. So we propose also some guideline that if SRMR is not lesser than 0.08, and then it's not lesser, then you must look into traditional PLS. Okay, if your SRMR pass, okay, if your SRMR pass, and your other fit criteria such as the test of exact fit shows that lesser than 95% and 99 bootstrap confidence, the quantile, then we can confirm that your model fit. So when your model fit, we can actually look into the consistent PLSC, which the estimation of consistent PLSC will be different because you're going to report roughly the same in terms of the measurement model, but the reliability, you need to report Dijkstra-Henselaar row A. In terms of structural model, you need to estimate model fit. Okay, model fit is important. I'm going to show back to you on the structural model, show back to you on the SmartPLS where to get this model fit result. So I strongly recommend you to read that paper. Yeah, if you have cited, if you can cite, then that would be perfect. Yeah, so that is PLSC. I have shown you all. Let's just try apply. But before that, I want to go back to SmartPLS. Okay, let us go back to SmartPLS again. I'll tell you about the model fit stuff. So the model fit, in this model fit, just now we run the PLS algorithm, right? The PLSC algorithm, as you can see here, PLS-FC algorithm. You click report, you will have your model fit. Okay, in model fit, you have two types of model fit. One is the saturated model, one is called the estimated model. The saturated model is always your measurement model. Your estimated model is always your structural model. What we want, the SRMR value of your model must lesser than 0.08. If it's lesser than 0.08, maybe it somehow give you a good indication to tell you that your construct that you use probably is a true reflective or common factor, Therefore, you need to run a PLS consistent, and your NFI, you must 0.9. But some they say that if you know, you must get 0.9 and above. Here is right, roughly almost 0.9. So it's still okay to somehow tell that your NFI is somehow explained that your reflective is a true reflective or common factor. And in terms of how to chi-square, we just ignore, because in CB-SEM, chi-square is a bad indication to run. Let us look into another criteria. I don't know where another criteria. Oh, no. Let us look into the DULS and DG. Okay, let us look into the DULS and DG. This thing, how to run your DULS and DG. This is the bootstrap test of exact fit. Okay, this is a new criteria of model fit proposed by Dijkstra and Hensler on DULS and DG. So I'm going to show you how to run. To run on your DULS and DG is very simple. You just need to run calculate, and you need to do a consistent PLS algorithm, run a consistent PLS bootstrapping, and here you go. You get your results in a very quick manner. Give me a second. Yep. Okay, you get your result. In these results, you will have, I think, yeah, it never produced here. Okay, it never produced here, but you can do another way. You just run a bootstrapping, normal bootstrapping. Then you do a complete, I know why it never produced. I never changed to complete bootstrapping. Yeah. Sorry, I never changed to complete. Run a consistent PLS bootstrapping. Your bootstrapping here must change to complete bootstrapping. Sorry, you need to change to complete bootstrapping in order for you to produce the DULS and DG, the test of exact fit bootstrapping results. And you run. I think now it will work. Give me a second, because when you run the complete bootstrapping, it will take some time. Any question you can throw to me in the chat while waiting for the results? I think, yeah, I get the results. Okay, in this result right now, yeah, you can see I run my SRMR, I have my DULS and DG. SRMR, you can run the bootstrap, but not necessarily you can look into just the value of 0.056. But right now, it is red color. It means worse. It means that your model does not fit, regardless measurement and structural. Why? The 0.056 value is actually, it is higher than the value of 95 and 99. What you want is to get lesser. Okay, lesser the value, which means that your model confirmed. Okay, this is the way of reading or interpret the data of the bootstrap of SRMR. Same with your DULS, same with your DG. Okay, same with your DULS, same with your DG. So in DULS, you can see the value you get for measurement model is 173, estimated model 173, and right now the value is higher than 95 and 99. So when it is higher, then your model does not fit. So in such a case, based on just now this model, we can clearly claim that you can run PLSC, but then your model does not fit. Then, sorry to say, your model does not show true reflective. Although it's a reflective construct, it does not really show true reflective because your data does not say so. So when your data does not say so, it is somehow tell you that you should use the traditional PLS. Why? Because maybe composite modeling can tell you a better story and scenario. Okay, because of these things that I have explained, I will move to my slide again. Back to my slide, I will explain back why does the result mention such a way. So back to my slide. Yeah. Okay. So back to the fundamental. What I always like to say is always back to the fundamental. You have right now a lot of debate on like CFA, CCA. At the end of the day, they are statisticians. They have the right whatever they say, and they run the simulation. They have, I mean, they are statisticians. But back to the most fundamental in research, that research design always comes first before. Okay, I always say that research design always comes first before statistics, especially when we are talking about empirical research. We are not talking about method research. We are not talking about statistical research. Okay, we are talking about empirical research. Research design comes first. Okay, sometimes we are not sure how respondents answer our questionnaire and our survey, and sometimes our data could skew to one side, because especially when you collect data in Malaysia, you rarely see Malaysia give you a normal distribution type of data where if you use a Likert scale 1, 2, 3, 4, 5, they will answer all the response 1, 2, 3, 4, 5. because we are in Malaysia and data collection in Malaysia, and we have collectivist culture, and then you can see most of our data that we get was skewed to a certain agreement. Like for example, 1, 2, 3, 4, 5, you collect Malaysia about satisfaction, then most of the time you will see the satisfaction answer to you is like 3, 4, 5. So in such a case, this is something that you need to rethink and rethink, okay? Because moving back to PLS consistent, there are a lot of uncertainty, still a lot of uncertainty. If you can look back in the Dijkstra-Henselaar, looking back at the simulation, their simulation is assumed the world to be perfect. Therefore, with that world to be perfect, with good loading, with that loading simulation, with the multivariate normal distribution in terms of the simulation, PLSC always tends to produce better result compared to the traditional PLS when we talk about reflective. So you need to rethink and rethink. That's what I can say as a researcher. Don't just blindly like, oh, when there's a literature come out, you just follow blindly. I'm not trying to say that I'm very good to give you any advice that whether to use PLSC or the traditional PLS to run reflective. But back to the most fundamental, okay, that if you think that your world is more on theory testing, confirmatory explanatory modeling, then you use CB-SEM and PLSC, especially when you assume that you are having a true reflective, okay? But when you are moving into more on prediction, where, sometimes I saw people to do a research like, oh, I reduce a PLS and then I follow up by artificial neural network. And again, I like artificial neural network idea, but artificial neural network idea is like more on pure prediction. When we talk about pure prediction, we are talking about machine learning. When we're talking about machine learning, we are assuming the theory is actually incorrect. We don't care about theory at all. Theory is hopeless. We don't care theory. We just run based on our data, like using big data. We run our data, and when the result produced in such a way, then we claim that the world works in that way. But PLS, interplay or maybe stand in between of the confirmatory world as well as prediction world. It stands in the middle. So the question here is, why not PLS? You can do confirmatory, it's fine, but then sometimes your data don't explain in a common factor world. Your data could explain in prediction world a bit. So when your data explain in such manner, why not PLS? So therefore, the first thing as a researcher, if you want to move into SEM, you want to learn more about SEM, is you need to understand what is factor-based SEM, and it uses common factor, which means it focuses on common variance only. But when we talk about composite-based method, if it is based on weighted sum for same purpose, the same purpose here is based on total variance, where it covers unit variance and common variance. And because it covers everything, it can get the best of the two worlds, explanatory as well as prediction. I'm not talking about confirmatory. I'm talking about explanatory as well as prediction, the best of two worlds. But if you think that you do not need the prediction, you just want to confirm stuff, then by all means, you can use PLSC. So that is my advice. The second advice you need to rethink is like, again, look into the construct that we have the Q, V, S, and so on. And you can see the red color circle. The red color circle is somehow related to the Earth that I mentioned just now. QVS is based on the concept that you really want to study. But sometimes the data that we collected, which is the observed variable that we collected, and this observed variable that we want to represent a proxy of a variable, regardless composite or factor, we always have the issue of residual. But once we get the latent variable score of composite factor, we will then have another issue called uncertainty. The uncertainty is the situation where your model does not fit. When your model does not fit, probably you should look into composite, where it calculates in a different manner, different estimation, it assumes total variance. So in such a way, you need to know the difference between factor-based view and composite-based view, okay? So this is something that you need to know, because composite-based view look into total variance, and if you talk about factor-based view, it looks into common variance. And again, sometimes this uncertainty is very hard to achieve, because when you look into the factor-based, which is the common variance world, when you save into a score based on a factor, true reflective factor score, the factor score have an issue called factor indeterminacy, When we talk about factor indeterminacy, this is another topic where you will not have a true value, true absolute score. You have an infinite score. Infinity score means that that score itself cannot do for prediction, only can do confirmatory. So that's another topic. But what I want to highlight to you is sometimes your model does not fit. What I want to highlight to you in a simple way, you run a PLS consistent. You assume it is a true reflective based on, you know that reflective is usually perception and behavioral study. You run, you get your loading, fantastic. You get the true correlation value, fantastic, using PLSC. But then your model fit fail. When your model fit fail, maybe it's a good indication to tell you that you probably should look into the composite world, which is just run a normal PLS and you'll get a result. And that's where Hare et al. 2020 mentioned that it is confirmatory composite analysis world. Yeah, so that is somehow in his view. So another view is like last one, Suster et al. 2016 also run a simulation study using an coefficient mean absolute error in a common factor model situation, which means that they run a simulation, assume that if I would have a construct and those construct have reflective construct, and we assume common factor, which means that the construct is a true reflective construct, and I run the traditional PLS as well as I run the PLS-Consistent. They do a simulation with different observation, which means different sample size, different loading, and same loading with 2 indicators, 4 indicators, 8 indicators with different situation. They found that when you run using PLS-C, okay, it will give you best estimation if your sample size is less than 250. But if you can see the red color circle there, the value of MAE for PLS compared to PLS-C as well as the CB-SEM, the result clearly shows that even you know that the model is common factor, a true reflective, but you just run traditional PLS, not the PLS-C, your error of your result is much more smaller compared to you to run PLS-C as well as CB-SEM estimation. Why? Because according to Herman Wood, back to the most fundamental, Herman Wood have once mentioned, if the sample size is getting larger and you have large number of indicators, your errors that produce in using traditional PLS to estimate reflective construct will be lesser. And therefore, this is also another good paper by Suster et al. Mentioned that you can still use the traditional PLS even you know that you are doing perception study for your reflective construct. So therefore, I think I would not want to explain another diagram, but I could somehow end my case here. That to use PLSC and PLS, you need to think twice. Okay, whether you believe in a confirmatory world or you want to use traditional PLS and you believe in explain while predicting, then that will be a different topic. Okay, so what's next? If you want to know more about the world of prediction, recently my colleague and I just published in this INDS paper, excuse me, INDS paper regarding causal prediction. You can take a look in this paper. This explain when to use prediction as well as confirmatory, and also talk about something more on model comparison. So you can take a look. It is in my SEM. You can actually get this paper easily. Okay, that's all. I'm almost there. For network, you can join my SEM, and right now my SEM is more than 6,000 groups.
Jacky, we can't hear you, Jacky.
Yeah, can you hear me?
Yeah, now okay.
So back to my screen. I think here, if you want to learn more about causal prediction regarding PLS, you can look into this latest article published with my co-authors in Industry Management Data System. It's about method paper, how we see PLS, how we view PLS as a causal prediction, but still model fit makes sense. But then in certain situations, when your data does not get model fit, then probably some of the prediction part is important. So you can look into this article. And then I'm almost there. And yeah, we have MySEM. I hope once you have attended this talk, you could learn more by joining MySEM. Right now, I think our group members already 6,000 plus, almost 7,000. So feel free to join. And on top of that, I will post something in the chat later. I think I post now. We have another YouTube link, which is called Research Land. Research, I think, Hiram, you type, you're on, you type. It's a Research Land. You can join YouTube. We have all the good stuff in method and maybe research in Research Land. YouTube, you can subscribe to it and you can learn a lot of stuff from there. And that's it from me. I hope you gain something. Feel free to ask me questions and you can feel free to contact me. Of course, you can Facebook me also and email to me to my Gmail. Yeah, that's all.
Okay, thank you, Jacky.